Okay, guys. Thank you. All right. So in the last half hour of this lecture, I'm going to do the derivation of the grand canonical distribution. For those of you who have already seen me do the canonical distribution, then this follows exactly the same mechanics, and this will be a boring lecture. If you haven't done it yourself already, I strongly suggest that you either do the canonical or the grand canonical, or both if you're that kind of keen, in order to know how to do these. So remember, I started off with the canonical distribution. I said, I'm going to have a whole bunch of identical systems. And then I said, let's connect them. These are identical systems, and that can just mean particles in boxes, or it could mean spin systems, containers of gas, but I have an incredibly large number of them. The canonical distribution, I just connected them. I said energy can be exchanged between these. They're identical systems, but energy can be exchanged. For the grand canonical distribution, I let them also exchange particles. Make little doors. You can all exchange particles like this. I'm making little doors, so the number of particles, they can move around between the different gas bottles. Each one would have an energy, a fixed volume, a variable number of particles, and everything else fixed. EI and NI can vary. Yeah? I have a huge number of systems. I'm using M for the number of systems now, but it's huge. M is so large that I will have several of these systems in the exact same microstate. And so I can define a probability of being in that microstate. And I will say that there is an average number of particles n is going to be the sum over all of those microstates with the probability that that microstates occur and the number of particles in that microstate. Just like I've got average energy is the sum over I of the probability of being in that microstate times the energy of that microstate. Yeah? But now my microstate includes different numbers of particles. Is clear? Any questions about that? Yeah, absolutely. Yep. Are they attempts to justify? So the question was, are the canonical and grand canonical distributions attempts to justify the probabilistic nature of things? No, I understand. I think the answer is like, not to attempts to justify, but if I say that we have an ensemble, then I need to start defining what, it's just a way of getting the definition of what probability means for this particular system. When I say to you, here is a container of gas, yeah? What is the probability of being in a particular microstate? You might fairly say to me, what do you mean probability? What does that mean? And I'll say to you, there's two ways of looking at it. One would be to have this thing go for a really long time and watch what happens to its microstate, see how it evolves, and then take the number of times that's in this particular configuration, or the amount of times in this particular configuration over the entire time. And I'll say, that's the probability of being in this particular microstate. And you'll be like, cool, that's a clear meaning of the word probability. Or I could say to you, imagine I have like a huge number of these, yeah? Some of them will be in this exact microstate, yeah? The number that are in that exact microstate divided by the total number is what I'm going to call the probability of being in the microstate I. So it's not just a matter of like, it's a matter of how do I define what probability means for this system? How do I make connection with a meaningful thing of probability? Yeah? Yeah. You can fix volume or pressure, not both. Not well, if you fix both and you have to fix the number of particles and their energy, right? So, okay, fix something like that. What else do you want to fix? Are they gases? Sure, if they're gases, then fix pressure. What about if they're spins? They have more spins going from one to the other? Sure, I can have a spin going from one to the other. That's not a problem. Yep. Maybe then there's no pressure at all. Maybe they're just, yeah. So they're just, whatever else is fixed. Fix what needs to be fixed. Render unto Caesar what is Caesar's. So we have average numbers of particles and average numbers of and average energies. And now what I need to do is I want to see what happens at equilibrium. How do I work out, right? So these sums over microstates I write this here for the people who can't be bothered turning up. Microstates I with probability PI. Yeah. So that's what these sums are over. Okay. I've got a equilibrium condition. How do I go from the equilibrium? How do I work out what happens at equilibrium that doesn't happen the rest of the time? What does equilibrium mean? Equilibrium means that each one of these boxes has the exact same number of particles and has the exact same energy, right? No! Gosh darn it! What does equilibrium mean? No! No. What is probability? What is the equilibrium condition? Not that all of them have the exact same macro state. Not that they all have the same micro state. But that the entropy is at the extremum. I maximize S. That's the key point. Maximize S at equilibrium. No. Yes, we'll find that out. Yes, but like there's an error there. There's a fluctuations. That's the whole point. Like, it's all going to be spread out. Yeah, you'd be surprised if it's not. Yeah. The highest probability is still going to turn out to be the one that has the lowest energy. That microstate that has the lowest energy is still going to be more probable. It's just that there's not going to be that many of those, and there's going to be lots of the ones that have the average energy. Yeah? Okay. This is really important. This is the whole point of statistical mechanics. We maximize the entropy. Maximize the amount of disorder. Actually an extremum, but whatever. So we want to maximize S subject to those constraints. Again, I'll write down, I think what I did last time, S over K. So let's do it again here. So exactly. So maximize S over K, call that F, subject to our conditions. The sum over all of the microstates of Pi equals 1. The sum over all of the microstates of Pi Ni is equal to the average number of particles. And the sum over I of Pi Ei is the average energy. So if I think about this system, I would take my bottles, they're all connected, and I would put in a bunch of energy, and I would put in a bunch of particles, and I'd wait to see what happens. I know what's going to happen. You're absolutely right. My fluctuations are going to be on order 1 over square root n. We worked that out before, but they're not identical. So important. So this is what we want to do. How do we do it? Write F equals minus sum over I of Pi log Pi. Then Lagrange multipliers alpha, beta, think I put a minus sign there in the notes, so I keep a minus sign here. It doesn't really matter, but let's put it with a minus sign. Beta and lambda for my third one. Here I was thinking to myself, I'll probably put gamma. No, lambda. Okay, I want to minimize this thing. So if I minimize df with all of the PIs and then have the 3 different constraints, then I'm going to be able to have a solution. So first thing I need to do is df dpi. Right? How do I do that? Well, I have to take this whole thing and take the derivative with respect to pi. The first term is sum over I p1 log p1 plus p2 log p2 plus p3 log p3. So one of the i's, let's say I equals 2, I could do derivative with respect to that particular I. All the other terms are going to be 0 because they don't depend on that particular pi. Only the ith one does. So the derivative of p log p with respect to p is log p and minus 1, because pi and then times the derivative of log pi. So that's the first term. Second term, alpha times the sum over I of pi minus 1. If I take the derivative of this thing with respect to pi, what do I get? This term. This term doesn't have a beta, this term. That's okay. Let's do it. We'll do it together. So I've done the first term already. Second term is minus alpha p1, p2, plus p3, plus p4, plus p5, and so on, minus 1. I take the derivative of this thing with respect to one of those pi's. What do I get? Minus alpha. It doesn't get that. There's a reason why I asked. Let me just write this one here as minus alpha p1 plus p2 plus p3 plus minus 1. Yeah? That's agreed so far? Yeah? Yeah. Now take the derivative of this thing with respect to p2. What do I get? What about if I take a derivative with respect to p3? What about p4? What about pi? Next term. Damn straight. Next term. Minus beta ei, because only the pi term matters. What about the last term? Yeah? How good is that? Derivative of this thing, if I want to maximize f, has to be 0. How many equations are represented here? How many equations are represented here? N. 1 for I equals 1, 1 for I equals 2, 1 for I equals 3, 1 for I equals 4, all the way up to I equals n. I've got n equations represented here, 1 for each I. It's clear? Clear as mud. That's n equations. If I look at this equation for f at the top, f equals minus sum of I pi log pi minus alpha blah, 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 blah. How many variables do I have in it? How many free parameters am I trying to fix? No. What am I varying? What am I varying? The probabilities. I'm varying the probabilities. P1 to Pn. Yeah? I want to vary those probabilities, P1 to Pn, subject to the conditions. Sum of those probabilities equals 1. Pi Ni summed up equals n bar. And sum of Pi Ei is E bar. So I'm varying the probabilities, letting them be free, saying which one's the most probable. What's the probability of this microstate? What does the probability of this microstate need to be such that S is maximized? Okay, cool. How many free variables do I have? I have n probabilities, and I've just added 3 more, alpha, beta, and gamma. So I have now, how many? N plus 3 variables. How many equations do I need in order to solve n plus 3 equations? Sorry, n plus 3 variables? N plus 3. I've got, how many do I have? How many do I have so far? N. What's my other 3 that I need? At the top, exactly. So I've got that one, that's N. I've got 3 more up the top. So I've got this equation, sum Pi equals 1, etc. So now that I've got that, I can actually take that and just solve it for P. Let's write that. All right, log P I equals -1 minus alpha minus beta EI minus lambda NI. And so I can say that the probability is e to the power of -1 minus alpha minus beta EI minus lambda NI. Oh, that was a overexcited closing bracket. Yeah. So let's use the other ones. Sum over I of Pi is now equal to the sum over I of e to the -1 minus alpha minus beta EI minus lambda NI should be equal to 1. Cool. Let's define, this is just following exactly what we did before. We define curly z equals, guys, work out, and ladies at home, work out what curly z, how you draw curly z in such a way that when you're reading your own writing, you know the difference between a straight z and a curly z. Yeah? Maybe you want a little cross through this one and you'd be like, that's my curly z. Or maybe you just have some wiggles around that you yourself can recognize, irregardless of whether somebody else can recognize it or not. Yeah? Be able to read your own writing is a key aspect of being able to do physics. Decide for yourself what your z and your curly z look like. So we define this curly z equals e to the 1 plus alpha. And that is equal to, from the equation above, I can multiply that by e to the 1 plus alpha on both sides, and I'll get sum over I, e to the minus beta EI minus lambda NI. It is so close to our old partition function, it just has this extra lambda NI bit in the numerator. So it's looking good. This is called grand partition function. Or by some people, the grand sum, which I think is a better name. The grand sum. Okay, we've got 2 more equations to go. Sum over I of Pi EI is equal to 1 over curly z, sum over I, EI, e to the minus beta EI minus lambda NI And that thing has to be equal to the average energy. Similarly, I need sum over I of PINI equals 1 over curly Z, sum over I, NI, e to the minus beta EI minus lambda NI equals N bar. When we did the canonical distribution, we then had to work out what beta was and lambda was. Well, we didn't have lambda, we just had beta. What did we have to do in order to figure out what beta was? We found out that eventually we found out that beta for the canonical distribution was 1 over KT. How did we get to that? Does anyone remember? It was like nearly 2 weeks ago. Do we differentiate? We did do some differentiations, but differentiating alone does not tell us what things are. What was the physical principle that we apply in order to work out what beta was? We found it was 1 over KT. What's the physical principle? What did we actually have to do in order to understand what it was? Well, if you look at this thing, there's no temperature anywhere. Nowhere on this is temperature. Nowhere on this is temperature. In order to get temperature and other thermodynamic variables, I need to do thermodynamics. Who likes doing thermodynamics? Excellent. Correct response. I do not like doing thermodynamics, but that is what we need to do. We need to do thermodynamics. Okay. Let's write out that entropy again. S equals minus K sum over I of PI log PI equals. Now we know what the PIs are. We can write out our entropy. Sum over I, 1 over curly Z, e to the minus beta EI minus lambda NI. And now I need to take the logarithm of this thing. The logarithm of this thing is, how I take the logarithm of log PI, I need to take, firstly, I've got to take, so this is the PI, this is the PI. That's PI. I need to take log PI. Log PI is going to go here. Let's have a look what it looks like. It's going to be, firstly, the exponential. If I take the log of an exponential, I just get the exponent. Minus beta EI minus lambda NI. Good. But then there's another term. What's the other term? 1 over Z. How I take the logarithm of 1 over Z's? Just log Z. Yeah? Okay. So that is, that's got to be equal to, so take this guy, got PI, blah, blah, blah. That's S equals minus K. Let me write like this. Sum of I of minus K. I've got PI times minus beta EI minus lambda NI. Just that one. And then the next term is minus K sum over I of PI log curly Z. I'm just splitting it up like that for no good reason. Yeah? Multiplying. The first term here is just minus, no, K. Whoop, minus times minus is plus. I've got K beta Sum over I of pi ei is just E bar plus K lambda. Sum over I of pi ni is N bar minus K log Z, because that's just the constant, and sum over I pi equals 1. Yeah? I've lost a minus. Oh no, no, I haven't. Have I? No, it's good. It's good. Yeah. Plus, plus. Oh no, the last one should be plus. Yeah, okay. Cool. That's because that one should have been a plus. Okay. Great. Okay. So that's S in terms of now average energy, average number of things, and our partition function. And then we've got to do thermodynamic stuff. What time is it? 1:48. 7 minutes to sketch it out. 7 minutes. It's all we need. It's all we need. It's not all I need. I need more, don't I? Oh, I don't want to. All right. Oh man, I'm trying to find the cheat way of doing this one in 7 minutes. The longer I stand here staring at it, the more I'm running out of time. Definition of temperature. How do I define temperature? I might say something like this. 1 over T is defined as being ds dE bar holding N and V constant. Yeah. Okay. So let's do it. 1 over K ds dE holding N and V constant equals. I have to take the derivative of this thing with respect to energy. I get KB, K beta. Oh, I took 1 over K as well. So just beta. Right. I need to take the derivative of beta with respect to energy. I'm going to get rid of that bars because they're just going to be trouble now. So easy energy. Next term, I'm going to have to take N, dN, dE. I'm going to have to take, d lambda dE. D lambda. I don't know what lambda is yet. D lambda dE. I don't know what lambda is yet, right? We need to work that one out still. And then I need the derivative of log curly z with respect to energy. That's my derivatives. N is constant. N is held constant here on the left-hand side, yeah? Definition. But lambda, I don't know what it is. So I don't know if that one I can hold constant. Okay, equals beta plus E plus N d lambda d beta plus d log Z d beta times d beta dE. So far, so good. But now I have to show you that this stuff in here is equal to 0. And that therefore this thing is therefore equal to beta, which is 1 over KT. How do I show you that this stuff is equal to 0? Well, I need to, and by the way, that's exactly what happened last time as well. how do I do that? I'm going to quickly show it to you. So what I need to do is I need to do this. I write down curly Z equals, just writing it up here because I don't have enough space on the board for anything really fun. Right, nearly done. D curly Z, d beta equals, holding Ni constant, d beta of this thing equals, first term, I'm going to take a derivative with respect to beta. So I'm going to pull down a factor of EI. So I'm going to get minus the sum over I of EI, e to the minus beta, EI minus lambda NI. And then I've got the lambda. I'm not done yet. That's the thing. So I've got to do the lambda part as well. Sum over I. When I do the lambda, I'm going to pull down a factor of Ni, e to the minus beta EI minus lambda NI times d lambda d beta. So lambda can depend on can depend on beta as well. So I need to take the derivative with respect to lambda and then take the derivative of lambda with respect to beta. Like I've done there. And that is then equal to minus partition function times the average energy minus partition function times the average n d lambda d beta. And then I take this and I see that that is actually 1 over z d z d beta at constant n equals minus d log curly z d beta at constant n, same thing, is equal to minus e minus n bar d lambda d beta. Now look at that. It's exactly what I need to show that this thing here equals 0. Same. That guy. Magic. So that's the place to stop for today. But you know what? We get an extra hour tomorrow morning to finish it off. So good news. So here we got beta equals 1 over KT again. Thank the Lord for that, because if I had to remember 2 different definitions of beta would be all kinds of trouble. Beta is always 1 over KT. Yay! Didn't have to be the case, but sometimes we get lucky. So if you haven't picked up your marked up mid-session test, come tomorrow morning and pick it up. I'll actually send that email to that effect now to remind people to come pick it up. Yeah. Tomorrow morning, 9 a.m. See you all there.